The cosmos is built on unanswered questions. We are about to journey through 30 theories that could explain space's biggest mysteries. By the end, you will see the universe in a completely new way. We will explore why the laws of physics seem perfectly tuned for life and what happens to information swallowed by a black hole. This is a voyage from the edges of proven science to the frontiers of pure imagination, all driven by a single human impulse: wonder. What part of the universe's story feels most mysterious to you? This perfect tuning is the first great cosmic puzzle. Why does our universe seem custom-built for us? The fundamental numbers that govern reality, like the strength of gravity or the mass of an electron, are set with such incredible precision that even a tiny change would make stars, planets, and life itself impossible. This is called the fine-tuning problem, and it feels less like a discovery and more like a cosmic riddle left on our doorstep. One compelling answer suggests we are not alone in existence, but rather we are simply in the right neighborhood. This is the theory of the multiverse. Imagine not one universe, but an endless sea of them, a vast cosmic landscape where every possible version of physical law plays out. In most of these universes, the constants are all wrong, leading to quick collapse or eternal emptiness. But in at least one, purely by the staggering odds of infinite possibilities, the numbers lined up just right. That one is ours. Think of it like a cosmic lottery with an infinite number of tickets. Someone had to win, and we are living on the winning ticket. There are different ways scientists picture this multiverse. One comes from cosmic inflation, the idea that our universe underwent a rapid expansion just after the Big Bang. Some theories suggest this inflation never truly stops, but instead spawns new bubble universes endlessly, each with its own unique physics. Another vision comes from quantum mechanics, the many worlds interpretation, where every possible outcome of a quantum event actually happens, splitting reality into countless branching timelines. While these models differ, they share a breathtaking conclusion. Our universe, with all its beauty and complexity, might not be a unique miracle, but simply one possibility among an infinite tapestry of realities. But if the multiverse feels almost philosophical, our next mystery is anchored in the cold, hard data of observation. We know dark matter exists because the universe behaves as if it is filled with something we cannot see. Look at a galaxy spinning, its outer stars whipping around at speeds that should send them flying off into the void. Yet they do not. It is as if the galaxy is wrapped in an invisible, massive halo of something that provides the extra gravity to hold everything together. This same unseen mass bends the light from distant galaxies, a phenomenon called gravitational lensing, creating cosmic mirages that further prove its presence. This invisible elephant in the room makes up about 85% of all matter in the cosmos. So what is it made of? The leading suspects are not stars or planets, but exotic particles that barely interact with ordinary light or matter. Two prime candidates dominate the search. The first are called weakly interacting massive particles, or WIMP. As their name suggests, they would be heavy and only communicate with our world through gravity and the weak nuclear force, making them incredibly difficult to catch. The second candidate is the action, a hypothetical particle born from a solution to a different puzzle in particle physics. Actions would be trillions of times lighter than an electron, but could exist in such staggering numbers that they collectively account for the missing mass. To find them, scientists have turned the Earth itself into a trap. Deep underground, in abandoned mines and beneath mountains, ultra-sensitive detectors wait in profound silence, shielded from cosmic rays, hoping to register the faintest bump from a WIMP collision. In laboratories cooled to near absolute zero, other experiments search for the subtle whisper of an action converting into a photon in a powerful magnetic field. It is a global, decades-long treasure hunt for a substance that forms the cosmic scaffolding of every galaxy. a silent, unseen ocean through which all the stars and planets we see are merely sailing. Yet the hunt for dark matter particles, for all its ingenuity, rests on a single, profound assumption. What if we have been searching for a ghost that does not exist? There is a radical, elegant, and deeply controversial idea that flips the entire puzzle on its head. Perhaps nothing is missing at all. Instead, our understanding of gravity itself is incomplete. This is the theory of modified Newtonian dynamics, or MUND. It proposes a simple but staggering revision. What if Isaac Newton and Albert Einstein's laws of gravity, which work flawlessly here in our solar system, simply break down in the extreme environments of deep space? Specifically, in the vast, quiet outskirts of galaxies where the gravitational pull becomes incredibly faint, the rules might change. In these regions of extremely low acceleration, gravity could become slightly stronger than our equations predict. That extra little tug would then be enough to hold those fast-moving outer stars in place, no invisible matter required. It is not a missing ingredient, but a misprinted recipe. Think of it like listening to a familiar song played at a volume so low you can barely hear it. Your brain might struggle to make out the melody, filling in gaps that are not really there. MUND suggests our physics has been doing the same thing, inventing dark matter to explain a gravitational signal we are mishearing. The theory has had some striking successes. For certain types of galaxies, especially faint, diffuse ones, MUND predictions about their rotation match the observed data almost perfectly, often more neatly than some dark matter models. It solves the mystery with a tweak to a law, not an unseen universe of particles. But for every success, there is a formidable challenge. The most famous is an object in space called the bullet cluster. This is what astronomers see when two galaxy clusters collide in a cosmic wreck of unimaginable scale. The collision is so violent that the ordinary gas clouds smash together and slow down like two clouds of smoke merging. But the gravitational lensing maps show the bulk of the mass, the stuff that bends the light, has sailed right through the collision and now lies far away from the gas. This is exactly what you would expect if the mass were made of dark matter particles that barely interact with each other or with gas. They would pass through the crash unaffected. For MUND to explain this, it would need a complex and unconvincing add-on, essentially inventing a new type of matter anyway. So the debate rages. Is dark matter a hidden substance waiting to be found, or is it a cosmic illusion, a signpost pointing to a deeper law of gravity we have yet to write? This is not just academic. The answer reshapes our fundamental picture of what the universe is made of and what forces truly bind it together. That cosmic collision leaves us with a paradox of its own, a battle between two pillars of physics. But to find a conflict that truly shakes the foundations of reality, we must look not to colliding galaxies, but to the ultimate cosmic destroyers. Black holes present us with a puzzle so deep it threatened to unravel our understanding of the universe. It is called the black hole information paradox, and it began with a startling discovery by Stephen Hawking. He showed that black holes are not completely black. Due to strange quantum effects at their event horizons, they slowly leak radiation and evaporate over astronomical timescales. This Hawking radiation, however, carries a terrible implication. According to Einstein's general relativity, anything that crosses the event horizon is lost forever, crushed into the singularity. All the unique information about what fell in, whether it was a star, a book, or a person, is seemingly erased from the universe. But quantum mechanics has a sacred, non-negotiable rule. Information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must be preserved. So here is the paradox. If a black hole evaporates away entirely, leaving behind only a faint haze of generic Hawking radiation, what happened to all that unique information? Did it vanish, violating quantum law, Or is it somehow preserved in the radiation in a form so scrambled we could never decode it? For decades, this was the ultimate stalemate. Then, a breathtakingly strange idea emerged from the world of string theory, offering a solution that changes how we see reality itself. It is called the holographic principle. The principle proposes that all the information contained within any volume of space, including everything inside a black hole, is not stored within that volume at all. Instead, it is perfectly encoded on the lower dimensional boundary that surrounds it. A black hole's entire three-dimensional interior, with all its doomed matter, is described by information painted on its two-dimensional event horizon. Think of it like the security hologram on a credit card. That flat, shiny strip contains all the data needed to project a three-dimensional image. The hologram is not a picture of the object, it is the object translated into a different kind of code. In this cosmic view, our universe with its rich depth and volume might be a magnificent illusion. All the events, particles, and forces we experience could be the projection of information stored on a distant, two-dimensional surface at the edge of everything. For the black hole paradox, this offers an elegant escape. The information of what fell in is not lost in the singularity. It is smeared and stored on the event horizon, and as the black hole evaporates via Hawking radiation, that information is slowly, intricately released back into the universe. The information is preserved just in the most unexpected way imaginable. It means the universe might fundamentally be a cosmic narrative, a story written not in three dimensions, but in two, with our rich reality being nothing more than the most immersive read-through imaginable. This holographic view of reality suggests a universe of immense potential. Yet when we look out into that vast cosmic ocean, we find only silence. This silence is the next great mystery, and it has a name. Enrico Fermi, a physicist during a lunchtime conversation in the 1950s, captured it with a simple, devastating question: where is everybody? The universe is ancient, over 13 billion years old, and unimaginably large, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars are older than our Sun and have Earth-like planets orbiting in their habitable zones. Given these staggering numbers, intelligent life should have arisen many times over, and some civilizations should have become interstellar, perhaps even colonizing entire galaxies over millions of years. The math screams that we should see signs of them everywhere: engineers, radio signals, megastructures, but we see nothing. This glaring contradiction between the high probability of alien life and the utter lack of evidence for it is the Fermi paradox. One explanation for this cosmic quiet is not comforting, but it is chillingly logical. It is called the Great Filter. The idea is that somewhere on the path from a lifeless planet to a spacefaring civilization, there exists a developmental stage so improbably difficult, so deadly that it acts like a sieve. Almost every candidate gets filtered out. The critical, terrifying question is where this filter lies. Is it behind us or is it ahead of us? If the Great Filter is in our past, it means humanity has already beaten incredible odds. Perhaps the jump from non-living chemistry to simple, replicating life is astronomically rare. Or maybe the leap from single-celled organisms to complex, multicellular animals is the true bottleneck. In this scenario, the galaxy could be littered with sterile worlds and microbial ponds, but we are among the first or the only to have made it this far. The silence is then a sign of our incredible luck, but if the filter is ahead of us, the implications are far darker. It suggests that the hardest step is not becoming intelligent, but surviving that intelligence. The filter could be the point where a civilization gains the technological power to destroy itself, whether through nuclear war, engineered pandemics, runaway artificial intelligence, or ecological collapse, and almost invariably does. In this view, the eerie silence of the cosmos is not a sign of emptiness but a graveyard. every promising world eventually reaches a technological adolescence and then vanishes, leaving behind only static. This theory transforms the search for extraterrestrial life into a profoundly high-stakes diagnostic for our own species. Finding even simple bacterial life on Mars or Europa would be thrilling, but under the Great Filter framework, it could be a warning. It would suggest that the step from simple to complex life is not the filter, making it more likely that the dangerous filter still lies in our future. Conversely, if we find the ruins of an ancient dead civilization, even a fossil, it would be the most terrifying discovery in history, confirming that the filter is real and that it waits for all who rise. The Fermi paradox and the Great Filter force us to confront a fundamental question about our place in the cosmos. Are we the pioneers, or are we the next in a long line of candles about to be snuffed out? The answer may determine whether our story is a prologue or an epitaph. The silence of the cosmos makes our own existence here on Earth feel even more miraculous. How did life begin on this small, wet rock in the first place? The mystery of life's origins is one of the deepest we face. The standard story taught in schools is that around 4 billion years ago, in a primordial soup of chemicals energized by lightning or volcanic vents, the first self-replicating molecule somehow assembled by chance. But the odds of that happening from scratch, even over millions of years, seem astronomically low. What if life did not start here at all? What if it arrived ready-made, a passenger on a cosmic delivery system? This is the theory of panspermia. It proposes that the seeds of life, its basic building blocks or even hardy microorganisms, are common throughout the galaxy. These seeds then travel between star systems, hitching rides on asteroids, comets, or even specks of interstellar dust. When one of these vessels crashes into a young, habitable world like the early Earth, it inoculates it with life. The planet becomes a fertile garden, not the original greenhouse. The evidence for this is more compelling than you might think. We have found meteorites, chunks of rock from Mars and the asteroid belt that contain complex organic molecules. Amino acids, the very building blocks of proteins, have been discovered inside these space rocks. This proves that the raw ingredients for life can form in the harsh environment of space and survive a fiery descent through an atmosphere. Even more telling is the existence of extremophiles here on Earth. These are microbes that thrive in conditions we once thought were utterly sterile, in boiling deep sea vents, inside solid rock miles underground, or in the bitter cold and radiation of Antarctica. Scientists have placed these tough little organisms outside the International Space Station, exposed to the vacuum of space, extreme temperatures, and punishing cosmic radiation for years. Many of them survived. If a humble Earth microbe can endure that, then it is entirely plausible that similar life from another world could survive a long journey through space shielded inside a rock. Panspermia does not solve the ultimate mystery of how life first arose. It simply moves the laboratory from Earth to somewhere else in the galaxy. But this leads to an even more provocative twist on the idea, one that directly connects to the Fermi paradox. What if the seeding was not a random accident but a deliberate act? This concept is called directed panspermia. It suggests that an ancient, advanced civilization, perhaps facing its own extinction, deliberately sent capsules containing microbial life out into the galaxy. Their goal would be to ensure that their biological legacy, or at least the spark of life itself, would continue on other worlds. It is a cosmic message in a bottle, but instead of a note, the bottle contains the blueprint for all future evolution. Think of it like an interstellar gardener scattering seeds onto promising young planets. Under this theory, we are not the children of Earth alone, but the distant descendants of a lineage that began around another star, perhaps billions of years ago. Our entire evolutionary tree, from the first single-celled organism to the human brain pondering its own origins, could be the long-term result of a conscious act of cosmic sowing. It adds a profound layer of intrigue to our search for meaning. Are we a natural accident, or are we part of someone else's ancient, sprawling project? The answer may be written in our very DNA, a code within a code waiting to be deciphered. That profound question of cosmic origins was met with a potential answer in the summer of 1977, a signal so powerful and strange it was literally circled on a printout with the word "Wow." For 72 glorious seconds, the Big Ear radio telescope at Ohio State University recorded a narrowband radio burst at precisely the frequency hydrogen emits in space, a frequency scientists reasoned an advanced civilization might use as a universal beacon. The signal was not natural static. It was a pure, focused tone that rose and fell exactly as a transmission from a fixed point in space would as Earth rotated, peaking in intensity before fading away. It matched every expectation for an artificial signal from beyond our world, and then it vanished. Decades of follow-up searches aimed at that tiny patch of sky in the constellation Sagittarius have heard nothing but the usual cosmic whisper. The WOW signal stands alone, a single, enigmatic shout in the dark. So what was it? The lack of a repeat forces science to consider every possible natural explanation, a process that is both sobering and fascinating. One leading theory points to a comet. In 2016, an astronomer noted that two comets unknown in 1977 were in roughly the same area of sky when the signal was detected. Could a massive cloud of hydrogen gas released by a comet have been the source? While comets do emit hydrogen, the specifics do not quite fit. The WOW signal was extremely focused, while a comet's hydrogen cloud is vast and diffuse, and the frequency was too precise. The comet explanation, while clever, is widely considered unlikely. Could it have been a bizarre stellar event? Some stars, like flare stars, can emit intense bursts of radio energy, but these are usually broadband, a blast of noise across many frequencies, not a clean, narrow tone. A passing asteroid or space debris reflecting a human transmission back to Earth is another idea, but the signal's characteristics and duration make this a remote chance. Then there is the possibility of terrestrial interference, a satellite or secret military experiment that slipped into the telescope's field of view. Yet the Big Ear telescope was designed with two feed horns that listen to slightly different points in the sky a few minutes apart. A signal from Earth or a nearby satellite would have appeared in both horns almost simultaneously. The WOW signal only appeared in one, strongly suggesting it came from deep space. Each natural explanation chips away at the mystery, yet none provides a perfect, definitive fit. This is the essence of scientific rigor, a relentless process of elimination that, so far, has failed to eliminate the most thrilling possibility of all. The WOW signal remains the best candidate we have ever recorded for a potential hello from another mind. It is a reminder that in the search for cosmic company, a single, unexplained event can hold more power than 1,000 theories, a ghost of a signal that continues to ask its own silent, compelling question. The WOW signal's unanswered call leaves us contemplating the nature of a mind that could send it. But what is a mind, really? This question leads us from the vastness of space to the intricate universe within our own skulls, and to a theory that attempts to bridge them in a truly radical way. The hard problem of consciousness asks why and how physical processes in the brain give rise to subjective experience, the feeling of being. Why does the electrical storm of neurons firing result in the taste of chocolate, the color red, or the ache of loneliness? One audacious answer comes from the quantum consciousness hypothesis. It suggests that the answer does not lie in classical biology alone, but in the spooky, probabilistic world of quantum mechanics. The physicist Roger Penrose, along with the anesthesiologist Stuart Hameroff, proposed a specific mechanism. Deep inside your brain cells are structures called microtubules, tiny protein scaffolds that help give cells their shape. Penrose and Hameroff theorized that these microtubules are not just structural. They could be quantum computers. Within them, delicate quantum states where particles exist in multiple possibilities at once, could form, interact, and then collapse in a coordinated way. This orchestrated collapse, they argue, is not just neural noise, it is the very spark of a conscious moment. Each flicker of awareness corresponds to a quantum computation happening at the foundation of reality itself. This idea makes a profound connection to one of quantum mechanics' strangest features, the observer effect. In experiments like the famous double slit, a particle seems to exist as a probability wave, going through both slits at once until it is observed or measured. At that instant, the wave collapses into a single, definite particle at a specific location. The quantum consciousness hypothesis flips the traditional interpretation. It posits that it is not the measurement device that causes the collapse, but the presence of a conscious observer. In this view, consciousness is not a passive byproduct of the universe. It is an active participant, a fundamental force that literally shapes reality by resolving quantum possibilities into concrete facts. It is a stunning proposition that the inner world of our minds is woven into the fabric of the cosmos. Mainstream science, however, meets this idea with deep skepticism. Critics point out that the warm, wet, chaotic environment of the brain is the last place you would expect fragile quantum states to survive long enough to perform any meaningful computation. They argue that classical physics and complex neural networks are sufficient to explain the brain's workings, and that invoking quantum mechanics is an unnecessary complication. Yet, for all its controversy, the theory stands as a bold testament to our deepest intellectual yearning. It is an attempt to solve two monumental mysteries with one elegant, if unproven, stroke, linking the intimate mystery of self to the grand mystery of the universe, suggesting that in the end they may be the same story. But if consciousness itself is a quantum process, it forces a deeper question about the reality it perceives. What if the universe our minds observe is not the base level of existence, but a rendered construct, an elaborate facade of code? This is the simulation hypothesis, the idea that everything we experience is an artificial reality, a computer simulation run by a civilization vastly more advanced than our own. The argument was framed powerfully by the philosopher Nick Bostrom as a simple trilemma, three possibilities of which at least one must be true. First, almost all civilizations at our level of technological maturity go extinct before becoming capable of creating such simulations. Second, almost all advanced civilizations lose interest in creating simulations of their ancestors. Or third, we are almost certainly living in a simulation. The logic is stark. If even a tiny fraction of advanced civilizations survive and choose to run detailed ancestor simulations, the number of simulated realities would quickly dwarf the one original base reality. Statistically, any conscious being is far more likely to be a simulated mind than an organic one. It is a modern cosmological myth that replaces gods with programmers. The evidence proponents suggest might be hidden in the very fabric of physics. Look at quantum mechanics, the strange, probabilistic nature of particles that only resolve into definite states when observed could be seen as a cosmic optimization. Why render every single particle in perfect detail across the entire universe all the time? It would be computationally wasteful. Instead, the simulation only calculates the precise properties of a particle when something or someone is looking at it. Much like a video game only renders the graphics on the part of the screen you are currently viewing. These potential glitches in the matrix might extend further. Some physicists have speculated that if our universe is a simulation running on a finite computer, there might be a fundamental resolution limit to space-time, a pixel size for reality. We might detect this by studying the highest energy cosmic rays. When these rays travel across the universe, if space-time is perfectly smooth, they should arrive with a certain distribution of energies. But if there is a hidden granularity, a digital fuzziness at the smallest scale, it would subtly alter that distribution, leaving a fingerprint of the underlying code. Other tests could search for conservation laws that are not perfectly obeyed, or for mathematical patterns in the constants of nature that resemble the elegant, simplified equations a programmer might use. The simulation hypothesis is ultimately untestable in a definitive sense, but that is not its point. Its power lies in how it reframes our entire existential situation. It asks us to consider that the laws of physics are not fundamental truths, but the rules of the game, and that the mystifying quantum weirdness we grapple with might simply be the background processes of a cosmic computer. Whether you find it terrifying or liberating, it challenges the bedrock of what we call real, suggesting that our search for the universe's secrets might ultimately be a quest to understand the nature of the machine we are running on, and the intentions, if any, of whoever booted it up. The simulation hypothesis makes our reality feel fragile, a layer of code resting on something deeper. But what if that deeper layer is not a computer, but a cosmic factory endlessly producing new realities? To find that factory, we must rewind time to the very first fraction of a second after the Big Bang, to a theory that solved some of cosmology's greatest puzzles in one breathtaking swoop. This is cosmic inflation. Before inflation, our universe was unimaginably hot, dense, and tiny, a seething quantum foam. The classic Big Bang model struggled with two baffling observations. First, the horizon problem. Look at opposite ends of the observable universe. They are so far apart that light has not had enough time since the Big Bang to travel between them. They have never been in contact, never exchanged heat or information. Yet, when we measure the cosmic microwave background, the afterglow of the Big Bang, the temperature is exactly the same in every direction, to an astonishing precision of 1 part in 100,000. How could regions that were never connected possibly reach the same temperature? The second puzzle is the flatness problem. The geometry of our universe appears to be almost perfectly flat, like a vast, infinite sheet. But in the early universe, even a tiny deviation from perfect flatness would have been magnified enormously over billions of years of expansion. For our universe to be as flat as we see it today, its initial conditions had to be fine-tuned to an absurd degree, like balancing a pencil on its tip for 13 billion years. Cosmic inflation provides an elegant solution to both. The theory proposes that when the universe was only a trillionth of a trillionth of a trillionth of a second old, it underwent a brief, explosive period of exponential expansion. In a fleeting moment, a region smaller than a proton was stretched to a size larger than our entire observable universe. This solves the horizon problem because everything we see today was once crammed into that tiny, connected region, which had plenty of time to even out its temperature before being blown apart. It solves the flatness problem because this hyper-stretching acts like inflating a balloon to cosmic proportions. No matter what shape you start with, a small patch of any surface, when blown up to an enormous size, will appear perfectly flat to anyone living on it. Inflation smooths and flattens the universe by sheer, monumental scale. But the most profound implication of inflation is not how it began, but how it might end, or rather, how it might not end at all. This leads to the concept of eternal inflation. Imagine the inflationary process as a landscape. In most regions, inflation ends, the energy driving the expansion decays, and that region becomes a stable, hot, dense universe like our own Big Bang. But according to some models, inflation is inherently unstable in a quantum sense. In some pockets, by random quantum fluctuation, the inflationary process never stops. These regions continue expanding exponentially at a mind-boggling rate, far faster than the speed of light. Within this eternally inflating background, bubbles of stability will spontaneously form, like pockets of calm in a raging storm. Each of these bubbles is a separate universe with its own Big Bang, its own laws of physics determined by how the inflation energy decayed within it. Our entire cosmos, with all its hundreds of billions of galaxies, is just one such bubble in an infinite, frothing sea of inflating spacetime. Picture a pot of boiling water on a stove that never turns off. The roiling water is the eternally inflating background. The bubbles that rise to the surface, pop, and release steam are the individual universes being born, evolving, and perhaps fading away. We are inside one of those bubbles, completely unaware of the infinite cosmic foam churning just beyond the edge of our perception. This is the multiverse given a physical mechanism. It is no longer just a philosophical idea, but a direct, if untestable, prediction of our best theory for the origin of everything. The fine-tuning we marveled at earlier, the perfect numbers that allow for stars and life, finds a chillingly simple explanation here. In an infinite array of bubble universes, every possible combination of physical constants and laws will exist somewhere. We do not live in a special universe, we simply live in one of the rare bubbles where the numbers allowed creatures like us to arise and ask the question. Eternal inflation paints a picture of a universe endlessly giving birth to itself. Yet within our own cosmic bubble, a different, more mysterious force now holds the reins. Dark energy is the dominant component of our universe, making up about 68% of its total energy budget, and it is doing something profoundly strange. It is causing the expansion of space itself to accelerate. Think of the Big Bang as a cosmic explosion, hurling galaxies apart. For most of cosmic history, everyone expected the mutual gravitational pull of all that matter to be slowing that expansion down, like gravity tugging on a ball thrown upward. But in the late 1990s, two separate teams of astronomers, by observing distant supernova, made a Nobel Prize-winning discovery: the expansion is not slowing. It is speeding up. Something is pushing the galaxies apart harder and faster as time goes on. This something is dark energy. The simplest and currently favored explanation comes from an old idea of Einstein's, later called his greatest blunder. He introduced a cosmological constant, a uniform energy density woven into the fabric of empty space itself. This vacuum energy would exert a kind of negative pressure, causing space to stretch. Even if you removed every single particle, every photon, every speck of dust, this intrinsic energy of the void would remain, an immutable feature of the cosmos. It is a static, unchanging force, a fixed property of reality. But is it really that simple? Many theorists are uneasy with this explanation, because when we try to calculate the strength of this vacuum energy from quantum theory, the number we get is wrong. Not just a little wrong, but 120 orders of magnitude wrong. A discrepancy so vast it is the worst prediction in the history of science. This colossal failure suggests we might be missing something fundamental. This has led to alternative theories, the most prominent being quintessence. Unlike the static cosmological constant, quintessence is a dynamic energy field. Imagine it as a kind of cosmic fluid that permeates all of space, but whose density and pressure can change over time. It could have been weak in the early universe, allowing matter to clump into galaxies, then grow stronger to drive the acceleration we see today. It might even fluctuate in the future. This dynamism opens the door to fates for the cosmos far stranger than the one implied by a simple cosmological constant. If dark energy is truly a constant, the future is a long, cold, and lonely one called the Big Freeze. As acceleration continues unchecked, distant galaxies will be carried away from us faster and faster, eventually crossing a cosmic horizon where their light can no longer reach us. Over trillions of years, every galaxy beyond our own local group will vanish from the observable universe, their light stretched into undetectable infrared whispers and then fading to nothing. The sky will go dark, star formation will cease as galaxies run out of gas, and one by one, stars will burn out. Eventually, even black holes will evaporate via Hawking radiation. The universe will become an ever-expanding, nearly empty void at a temperature just above absolute zero, a state of maximum entropy where nothing happens forever. But if dark energy is quintessence, the future could be much more dramatic or much more terrifying. One possibility is the Big Rip. If the strength of dark energy increases over time, its repulsive force could eventually overcome not just the gravity between galaxies, but the forces holding galaxies, stars, planets, and even atoms themselves together. At a precise moment in the far future, every structure in the universe would be violently torn apart in a catastrophic cosmic unraveling. Another scenario is that the quintessence field could decay, its energy transforming into matter and radiation, potentially triggering a new cycle of cosmic inflation and a new Big Bang. We are left with a breathtaking uncertainty. The force that determines the ultimate fate of every galaxy, every star, and every atom in the cosmos is almost completely unknown to us. Is it the silent hum of empty space or a shifting fifth element, a quintessence, writing the final chapter of our universe's story in a script we have only just begun to read? That accelerating fate of the cosmos is written on the grandest of scales, but sometimes the most perplexing clues come from the smallest of nudges. For decades, two robotic pioneers sent a ghostly whisper back to Earth that defied explanation. The Pioneer 10 and Pioneer 11 spacecraft, after completing their historic missions to Jupiter and Saturn, continued their lonely journeys out of the solar system. As they sailed into the dark, mission scientists tracking their trajectories noticed something deeply odd. Both spacecraft were slowing down ever so slightly more than the laws of gravity predicted. It was a minuscule deceleration, a force about 10 billion times weaker than the gravity we feel on Earth, but it was persistent and identical for both probes. This was the Pioneer anomaly. For years, it was a tantalizing signal in the data, a hint that perhaps our understanding of gravity was failing in the deep, quiet reaches of interplanetary space. Could it be evidence of dark matter dragging on the probes? Was it a sign of a subtle flaw in Einstein's theory of general relativity? The anomaly became a classic space mystery, a tiny crack in the foundation of physics that invited wild speculation and rigorous study. The solution, however, did not lie in rewriting the laws of the universe. It was hidden in the mundane engineering of the spacecraft themselves, waiting for a detective with enough patience to see it. The breakthrough came from a team that decided to treat the Pioneers not just as scientific instruments, but as physical objects in space. They built incredibly detailed computer models of the spacecraft, accounting for every known force, from the gravitational tug of distant planets to the faint pressure of sunlight itself. Yet the anomaly remained. Then they considered heat. The Pioneers were powered by radioactive thermoelectric generators, essentially nuclear batteries that produced heat as they decayed. That heat had to go somewhere, and it radiated away from the spacecraft as infrared light. The key insight was that this radiation was not perfectly even. The spacecraft were designed with their main antennae always pointed back at Earth, which meant their large dish-shaped bodies acted like shields. More heat was escaping from the back of the craft, radiating out into space from the warm power units than from the front, which was pointed sunward and also had the antenna structure blocking emission. This uneven or anisotropic thermal radiation created a tiny but constant thrust in the opposite direction. Picture a car with a single brake pad that is always ever so lightly touching the wheel. The effect is negligible in a short drive, but over an interstellar journey spanning billions of miles, that tiny, constant push backward adds up to a measurable deceleration. The numbers matched perfectly. The mysterious force slowing the Pioneers was not a new law of physics, but the gentle, cumulative kick of their own waste heat. The case was closed not with a grand new theory, but with painstaking accounting. This resolution is a quiet triumph for the scientific process. It celebrates a different kind of discovery, the victory of meticulous detail over sensational mystery. The universe often speaks in whispers, and the Pioneer anomaly reminds us that before we invoke dark forces or rewritten laws, we must first listen very, very closely to the hum of our own machines. It is a lesson in humility and rigor, proving that sometimes the most profound truth is that there is no magic, only physics we had not yet fully counted. The pioneers' solved anomaly shows how easily we can misread a faint cosmic signal. But sometimes a signal is not faint at all. It arrives from the depths of interstellar space, a visitor so strange it ignited one of the fiercest scientific debates of our time. In October 2017, astronomers in Hawaii spotted a point of light moving at blistering speed. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. This was no asteroid from our own solar system. It was the first confirmed interstellar object ever observed, a cosmic wanderer from another star. They named it Oumuamua, Hawaiian for scout or messenger from the distant past. The data that came back was perplexing. First, its shape. Based on extreme variations in its brightness as it tumbled, astronomers deduced it was not round, but wildly elongated, perhaps 10 times as long as it was wide. Imagine a cosmic cigar or a pancake tumbling through the void. Second, it showed no coma, the fuzzy halo of gas and dust that forms around comets when they approach the sun. This suggested it was a rocky or metallic asteroid, not an icy comet. But then came the third and most baffling clue. Precise tracking revealed Oumuamua was accelerating away from the sun, deviating slightly from the path predicted by gravity alone. Comets do this all the time as sunlight vaporizes their ice, creating jets of gas that act like tiny thrusters. But Oumuamua had no visible coma, no detectable outgassing. So what was pushing it? This trifecta of oddities, the shape, the lack of a coma, and the mysterious acceleration, made Oumuamua a true scientific enigma. Enter Harvard astronomer Avi Loeb with a provocative hypothesis. Could Oumuamua be artificial? He suggested its peculiar acceleration could be explained if it were an extremely thin, lightweight object pushed by the pressure of sunlight itself, a kind of natural light sail. Its unusual shape would be consistent with such a design. Loeb argued we should at least consider the possibility that Oumuamua was a piece of advanced technology, perhaps a defunct probe or a discarded piece of a larger structure drifting through our cosmic neighborhood. The idea captured the public imagination, framing Oumuamua as a potential artifact from an alien civilization. The scientific community, however, largely responded with intense skepticism. Extraordinary claims require extraordinary evidence, and most researchers argued that natural explanations, while still being worked out, were far more likely. They pointed out that we had never seen an interstellar object before, so our expectations of what is normal were built on a sample size of one. The quest for a natural explanation led to fascinating possibilities. One prominent theory is that Oumuamua was a chunk of solid molecular hydrogen ice. Such an iceberg, born in the cold core of a giant molecular cloud, would not form a dusty coma like a water comet, and as it approached the sun, the sublimating hydrogen gas could have provided the unseen thrust. Another compelling idea, published in a major journal, proposed it was a fragment of a Pluto-like world from another solar system, a chunk of nitrogen ice. As the sun warmed one side, nitrogen would have vaporized, jetting off and accelerating the object exactly as observed, while leaving no dusty debris. Its flattened shape could have come from the way such exotic ices erode. The debate over Oumuamua is not a battle between open-mindedness and closed-mindedness. It is a perfect case study in how science operates at the frontier. On one side, a theorist pushes the boundaries of possibility, urging us not to dismiss a potentially paradigm-shattering idea simply because it sounds like science fiction. On the other, the majority of scientists demand that we exhaust every conceivable natural explanation, no matter how novel, before leaping to conclusions that rewrite our place in the cosmos. Oumuamua is now gone, speeding back into the interstellar dark, its true nature perhaps forever a mystery, but its legacy is a powerful reminder. the universe is capable of producing wonders so bizarre they challenge our very categories. The next scout that passes through may give us the answers, or it may pose an even deeper riddle. Oumuamua's silent passage reminds us that evidence for other minds could be subtle, even bizarre. But what would a truly advanced civilization look like? How would we even recognize its signature across the gulfs of space? A brilliant framework for thinking about this comes from the Soviet astronomer Nikolai Kardashev. He proposed a simple, elegant way to classify civilizations not by their politics or philosophy, but by their energy appetite. It is called the Kardashev scale. A Type 1 civilization has mastered all the energy available on its home planet, harnessing the power of volcanoes, weather, and sunlight that falls upon its world. Humanity is not quite there yet, but we are climbing toward this level. A Type 2 civilization is where the scale becomes truly cosmic. This civilization has achieved mastery over its entire star. It can capture and use every single watt of energy its sun produces. To do this, it would likely construct a megastructure of almost incomprehensible scale, a concept popularized by the physicist Freeman Dyson. The idea is not necessarily a solid shell, which would be mechanically impossible, but a Dyson swarm. Imagine millions or billions of giant solar collecting satellites, factories, and habitats, all orbiting the star in a dense, coordinated cloud. This swarm would capture the star's light, using it for computation, construction, and life support, and in the process, it would change the star's appearance in a fundamental way. From the outside, the star would not disappear, but it would grow dramatically dim in visible light as that light is absorbed by the swarm. However, energy cannot be created or destroyed, only transformed. All that captured stellar energy must eventually be used and then re-radiated as waste heat, which glows in the infrared part of the spectrum. So, to an astronomer light years away, a star surrounded by a Dyson swarm would look like a bizarre mismatch, a faint pinpoint in visible light paired with an intense, unnatural infrared signature. It would be a cosmic beacon screaming, "Technology here." This has given astronomers a concrete, if needle-in-a-haystack, search strategy. Projects like Glimpsing Heat from Alien Technologies, or GHT, have scanned millions of galaxies looking for this exact infrared excess. They search for entire galaxies that glow too brightly in infrared, which could hint at a Type 3 civilization, one that has harnessed the power of its entire galaxy. So far, the results have been quiet. No definitive smoking gun megastructure has been found. But this absence is not a failure, it is a profound data point in the Fermi paradox. The silence tells us that if such galaxy-spanning civilizations exist, they are exceedingly rare. More importantly, it suggests that the leap from a planetary to a stellar civilization from Type 1 to Type 2 might be the very great filter we feared. Building a Dyson swarm is an existential project. It requires a species to achieve complete planetary unity, overcome resource scarcity, and maintain stability for millennia, all while developing technologies we can barely dream of. Perhaps no civilization survives its own adolescence long enough to enshroud its star. Or perhaps they do, but their technology becomes so efficient that their waste heat signature is minimized, rendering them invisible to our crude searches. The ongoing hunt for Dyson swarms is more than a search for alien engineering. It is a test of our own cosmic potential. Are the stars destined to remain naked fires in the dark, or is the universe quietly dotted with encapsulated suns, each a testament to a species that learned to build on a scale worthy of the cosmos? The answer, written in missing infrared light, will tell us if the future we imagine is a fantasy or a blueprint. The search for cosmic megastructures is a hunt for intelligence on a grand scale, but the universe may have its own ready-made shortcuts. Einstein's theory of general relativity, our best description of gravity, contains mathematical solutions far stranger than black holes. Two of the most mind-bending are white holes and wormholes. A white hole is essentially the theoretical opposite of a black hole. Where a black hole's event horizon is a point of no return, a one-way street into oblivion, a white hole's horizon would be a point of no entry. Nothing from the outside could ever cross in. Instead, matter and energy could only erupt outward from its interior. Think of it as a cosmic fountain or a black hole running in reverse. If you were to watch a film of matter falling into a black hole and then play that film backwards, you would see a white hole violently spewing that matter back into the universe. This makes white holes incredibly appealing as a potential source for unexplained cosmic explosions, or even as the origin of our own Big Bang. However, most physicists consider them to be mathematical curiosities rather than real objects. They violate the second law of thermodynamics, which dictates that disorder always increases. A white hole, by spontaneously ejecting ordered matter, would be a source of order, not chaos. More critically, they are thought to be profoundly unstable. The moment any stray speck of dust tried to fall in, the delicate equations would collapse and the white hole would instantly transform into a black hole. So while they dance elegantly in the mathematics, they likely flicker out of existence before they can ever form in reality. Yet, if you take the concept of a black hole and a white hole and connect them, you get something even more fantastic, a wormhole. Formerly called an Einstein-Rosen bridge, a wormhole is a theoretical tunnel through the fabric of space-time. Picture the universe not as a flat sheet, but as a folded piece of paper. The distance between 2 points on the fold might be vast across the surface, but a wormhole would be like a pencil poking through the paper, creating a shortcut between them. This is not science fiction, it is a valid, if exotic, solution to Einstein's equations. A simple, natural wormhole would be a connection between a black hole in one region of space and a white hole in another. But given the instability of white holes, such a structure would be fleeting, snapping shut in an instant. For a wormhole to be traversable, to become a stable tunnel for interstellar travel, it would require something truly bizarre holding it open, exotic matter. This is not just unusual stuff, it is matter that possesses negative energy density. It would have a kind of anti-gravitational effect, pushing the walls of the wormhole apart to prevent its collapse. We have hints that such exotic matter might exist in tiny quantities due to quantum effects, like the Casimir effect, where the energy of empty space between two very close metal plates becomes slightly negative. But the amount needed to stabilize a wormhole large enough for a spaceship is astronomical, far beyond anything we can conceive of creating. Furthermore, even if you could open one, the radiation and tidal forces inside would likely be lethal, and the simple act of a single photon passing through could destabilize the entire structure. So while wormholes captivate our dreams of galactic exploration, they remain firmly in the realm of theoretical possibility. They are a reminder that the universe's blueprint allows for wonders we can describe but may never touch, cosmic architecture written into the laws of physics, waiting for a builder with tools we cannot yet imagine. Wormholes are cosmic shortcuts written in mathematics, but they lead to a place where mathematics itself fails. At the very center of a black hole, according to Einstein's general relativity, lies the singularity. This is not a place you can point to on a map. It is a moment in time, a point of infinite density where all the mass that ever fell into the black hole is crushed into a volume of zero size. Here, gravity becomes infinite, the curvature of space-time becomes infinite, and our equations simply spit out nonsense. The laws of physics as we know them break down completely. This is more than a mystery, it is a screaming alarm that our understanding of reality is incomplete. The singularity represents the ultimate clash between our two most successful theories. General relativity, which masterfully describes the gravity of planets, stars, and galaxies, paints the cosmos as a smooth, curving fabric. Quantum mechanics, which flawlessly predicts the behavior of atoms and particles, tells us that at the tiniest scales, everything is grainy, probabilistic, and uncertain. These two pillars of modern physics are fundamentally incompatible. One cannot handle the infinitely small, and the other cannot handle gravity. The singularity is where this civil war in physics comes to a head. To resolve it, we need a theory that can do both, a single framework that describes gravity using the rules of the quantum world. This holy grail is called a theory of quantum gravity. It is the quest to rewrite the laws of the universe for the most extreme conditions imaginable. Two of the most prominent contenders offer radically different visions of what replaces that terrifying point of infinity. The first is loop quantum gravity. This approach takes the fabric of space-time very literally. It proposes that space is not smooth and continuous, but woven from tiny, finite loops, a network of intersecting threads of gravitational field. These loops are unimaginably small at the Planck scale, about 10 to the power of -35 meters. In this view, there is a smallest possible piece of space, a quantum of volume, just as light comes in quanta called photons. So what happens at the heart of a black hole? There is no infinite crush. Instead, when matter is compressed to this ultimate density, the repulsive force of these quantum loops becomes overwhelming. The collapse reverses. The singularity becomes a quantum bounce. The dying star's core, instead of vanishing into nothingness, rebounds, potentially spewing its material out into a new region of spacetime. It is as if the black hole leads not to oblivion but to a cosmic rebirth, a doorway to another universe. The second great contender is string theory. Here, the fundamental ingredients of reality are not point-like particles, but incredibly tiny, vibrating strings. Different vibrations correspond to different particles, like notes on a guitar string. In this framework, the singularity is also banished. As you approach the center, the strings that make up matter and the very fabric of space-time become so agitated and tangled that the classical idea of a point disappears. The core becomes a fuzzy, hot, dense ball of stringy matter, often described as a fuzzball. There is no sharp boundary, no infinite density, just a turbulent quantum soup where our familiar notions of here and now dissolve. This is the true frontier of physics, a realm where space and time themselves may be emergent properties, illusions that arise from a deeper, more fundamental layer of reality we have yet to comprehend. The quest to kill the singularity is not just about fixing a mathematical error. It is about answering the most profound question we can ask. What are the foundational rules of existence in a place where existence, as we define it, ends? The singularities of black holes force us to confront the limits of our knowledge. Yet, a very different kind of silence, not from gravity's abyss but from the stars themselves, may have a more sociological explanation. If the universe is so vast and old, where is everyone? The zoo hypothesis offers a startlingly simple and somewhat humbling answer. It suggests that advanced extraterrestrial civilizations are fully aware of our existence, but have deliberately chosen not to make contact. They are observing us just as we observe animals in a protected wildlife reserve or creatures in a zoo. We are the exhibit, and they are the quiet, unseen visitors on the other side of a one-way mirror. This idea is deeply tied to another popular concept from science fiction, a galactic prime directive, a non-interference policy that prevents more developed societies from influencing the natural, cultural, and technological evolution of younger ones. The reasoning behind such a rule could be ethical, scientific, or even practical. From an ethical standpoint, a truly advanced civilization might see contact as a form of cosmic colonialism, an act that would irrevocably shatter our culture, our religions, and our sense of self. It would be like a modern anthropologist landing a helicopter in the middle of an uncontacted tribe in the Amazon, an act of profound violence no matter how good the intentions. Scientifically, we are a fascinating, uncontrolled experiment. A civilization that has mastered the stars might find immense value in watching a young species develop naturally, without outside influence, to study the universal patterns of intelligence, society, and technology. Our entire history, with all its wars, art, and discoveries, is a unique data set. Making contact would corrupt the experiment. There are darker, more pragmatic versions of this idea, sometimes called the interstellar quarantine or the planetary park hypothesis. Perhaps we are not in a zoo, but in a dangerous jungle, and the fence is there to protect them. A young, volatile species like ours, with nuclear weapons and a history of conflict, might be viewed as inherently dangerous, a potential galactic pathogen. Advanced societies may have agreed to cordon us off until we prove we can overcome our self-destructive tendencies and achieve a stable, global maturity. Or the fence might be for our own protection, shielding us from a wider galactic community that is far more perilous than we realize. The implications of this theory are profound for our cosmic self-image. It transforms the Fermi paradox from a question of absence into one of deliberate silence. The stars are not empty, they are full of watchers. This reframes every unexplained light in the sky, every strange radio signal we cannot decipher. They might not be attempts to say hello, but the equivalent of a researcher's notebook, a passive sensor gathering data. It suggests a universe that is not lonely but curated. Are we an isolated experiment in a cosmic lab, or are we being patiently watched, waiting for the day we pass some unseen test and the keepers finally open the gate? The answer to that question changes everything about what it means to grow up as a species. The idea of a cosmic zoo places our universe within a grand, silent narrative. But what if the story itself is not linear, but a loop, a tale told again and again? Our prevailing story of the cosmos begins with a single, explosive origin, the Big Bang, and points toward an end in cold, dark emptiness. Yet an ancient and compelling alternative whispers that this might be just one act in an endless cosmic play. This is the theory of the cyclic universe, a vision where the cosmos knows no true beginning and no final end, only an eternal rhythm of death and rebirth. The classic version of this idea is the Big Crunch. Imagine the expansion of the universe driven by the Big Bang, gradually slowing down as gravity pulls everything back together. Over trillions of years, galaxies would reverse their flight, drawing nearer and nearer. The sky would grow hotter and brighter as the cosmic background radiation is blue-shifted. Eventually, all matter and energy would be compressed into an unimaginably hot, dense state, a mirror image of the Big Bang itself. In this model, the universe ends not with a whimper, but with a catastrophic implosion, a singularity that could then, perhaps, trigger another Big Bang, starting the cycle anew. It is a poetic symmetry, a cosmic heartbeat. For a time, this was a legitimate contender for our fate. But then, in the late 1990s, astronomers discovered dark energy and the accelerating expansion of the universe. This observation seemed to slam the door on the Big Crunch. If space itself is being pushed apart faster and faster, gravity can never win the tug of war. The universe appears destined for that cold, lonely Big Freeze, not a fiery reunion. However, the dream of a cyclic universe did not die, it evolved. Enter its modern, more sophisticated incarnation, the Big Bounce. This theory, emerging from cutting-edge ideas like loop quantum cosmology, agrees that our current expansion is accelerating and will likely continue for an eon. But it proposes that dark energy is not a permanent feature. Instead, it could be a temporary phase in a much longer cycle. In the far, far future, perhaps over timescales so vast they dwarf the current age of the universe, the nature of dark energy could transform. Its repulsive force might fade away or even reverse, becoming attractive. If that happens, the long era of acceleration would end and gravity would reassert its grip. The expansion would halt and the long contraction toward a Big Crunch would begin. But here is the crucial, beautiful twist offered by quantum gravity. In the classic Big Crunch, everything collapses into a singularity, a point of infinite density where physics breaks down and the story stops. The Big Bounce theory suggests that a quantum repulsion, a force arising from the granular nature of spacetime itself, becomes overwhelmingly powerful at that extreme density. Instead of reaching an infinite point, the collapsing universe hits a quantum wall and rebounds. It is like compressing a spring to its absolute limit. The energy stored then drives a new expansion, a new Big Bang. Our entire cosmos, with all its galaxies and laws, could be the aftermath of a previous universe's collapse, and we, in turn, may be the seed for the next. This stands in stark contrast to the prevailing inflationary model, which posits a single, unique beginning from a quantum fluctuation in a primordial void. One is a story with a definitive start, the other is a story without end, an eternal return. So how could we ever know if our universe is part of such a grand cycle? The evidence might be hidden in the oldest light we can see, the cosmic microwave background. A universe that has bounced would carry scars from its previous incarnation. The violent collapse and rebound could have created unique patterns, subtle imprints or anomalies in the temperature fluctuations of that afterglow. Some researchers have even suggested that the mysterious cold spot observed in the microwave background could be a bruise from a collision with a prior universe in a cyclic multiverse. Future, more sensitive space telescopes will map this radiation in exquisite detail, searching for these cosmic fingerprints. The answer to our deepest origin story may not lie in looking forward to an end, but in listening for the faint, reverberating echo of a universe that came before. KIC 8462852, better known as Tabby's star, offered a different kind of signal, one written not in radio waves but in stolen light. Nestled in the constellation Cygnus, this otherwise ordinary star began behaving in a way astronomers had never seen. Data from the Kepler Space Telescope revealed it was not just dimming, it was flickering erratically. Most planet-hunting stars show gentle, periodic dips when an orbiting world passes in front. Tabby's star did the opposite. Its light would plummet by staggering amounts, up to 22%, in chaotic, asymmetrical drops that lasted for days or weeks. Then it would partially recover, only to dip again in a completely different pattern. This was not the signature of a neat, round planet. It looked like something massive, jagged, and incomprehensible was drifting in front of the star, blocking its light in a bizarre, unnatural dance. The strangeness was so profound that when the data was published, scientists openly entertained a wild possibility. Could this be evidence of a Dyson swarm under construction? The irregular blocks of light perfectly matched what you might expect from a partially built megastructure, a vast array of solar collectors in chaotic formation around the star. For a moment, it seemed the cosmic zoo might have an architect we could actually see. The allure of that idea was magnetic, but science demands a relentless search for simpler answers. Astronomers turned every instrument they could toward that distant point of light, gathering more data across different wavelengths. The key clue came from studying how the dimming changed with color. If a solid object, like a planet or a megastructure panel, blocks a star's light, it typically blocks all colors equally. But if the blockage comes from diffused dust, the effect is different. Tiny dust particles scatter blue light more easily than red light. So when a dusty cloud passes in front, the star dims more in blue light than in red. That is exactly what subsequent observations of Tabby's star showed. The dimming was not uniform, it was chromatic. The star grew fainter more dramatically in blue wavelengths. This fingerprint pointed decisively away from solid alien engineering and toward a natural, if spectacular, cosmic cloud. The leading explanation now centers on a vast, uneven swarm of fine dust, likely the remnants of a catastrophic breakup. One compelling scenario involves a giant comet, or perhaps a family of comets, on a long, elliptical orbit around the star. As they swing close to the star's heat, they could be fragmenting violently, creating a sprawling cloud of debris that trails and spreads along their orbital path. Another possibility is the aftermath of a planetary collision. a cosmic crash that pulverized a moon or a planet into billions of dusty fragments now drifting in a chaotic disk. This dust cloud would be incredibly uneven, with dense clumps and tenuous veils, accounting for the star's erratic and deep dimming patterns. Continued long-term monitoring has reinforced this view. The star's overall brightness has also shown a very gradual, long-term decline over the past century, which fits with a larger, diffuse dust envelope slowly dispersing or settling into new orbits. The story of Tabby's star is a masterclass in how modern science navigates between wonder and rigor. It began with a genuinely baffling signal that justified asking an extraordinary question. The process then involved gathering more precise data, looking for the subtle fingerprints that distinguish a dust cloud from a metal plate. The answer, while less sensational than a Dyson swarm, is no less fascinating. It reveals a star system in the throes of dramatic, violent change, a place where worlds may be shattering and comets are disintegrating on a grand scale. It reminds us that the universe is capable of producing natural phenomena so odd they brush against the edges of science fiction, and that the patient work of explanation often reveals a reality more intricate and surprising than our first, most thrilling guesses. That flickering starlight reveals a cosmos of immense possibility, but it is in the tiniest of realms where possibility becomes law. The quantum world operates on probability, a dice game where particles exist in multiple states at once, a blur of potential until observed. This leads to a profound question. What happens to all those other possibilities when the dice finally land? One radical answer rewrites the entire story of reality. According to the many worlds interpretation of quantum mechanics proposed by physicist Hugh Everett, nothing is ever lost. Every time a quantum event has more than one possible outcome, the universe does not choose. Instead, it splits. Reality branches like a forking path, creating a new, parallel universe for every single possibility. In one branch, the radioactive atom decays. In another, it does not. Both outcomes happen with absolute certainty, but in separate, non-communicating worlds. This solves the infamous measurement problem, the mystery of why observation seems to collapse a probability wave into one definite result. In the many worlds view, there is no collapse, only division. The observer becomes entangled with the system, and their own reality splits as well. Think of the classic thought experiment of Schrödinger's cat. In the standard interpretation, the cat in the box is in a ghostly superposition of both alive and dead until someone looks, forcing a single, gruesome outcome. In the many worlds universe, there is no paradox. When the box is opened, reality splits in two. In one universe, you open the box and find a living cat relieved. In the parallel branch, an identical version of you opens the identical box and finds a dead cat horrified. Both events are equally real, but the two versions of you are now forever separated, each living out the consequences in their own stream of reality. The implications for our own lives are staggering. Every choice you make, from a monumental career decision to the seemingly random flick of a neuron, could be the site of a quantum split. In one branch, you turned left and met the love of your life. In another, you turned right and lived a completely different story. The cosmos becomes a vast, ever-branching tree of all possible histories, a tapestry woven from every decision ever made or not made by every conscious being and every random particle since the beginning of time. This raises haunting questions about free will and identity. If every possible version of you exists somewhere, does your specific path have any meaning? Are you the author of your life, or just one reader experiencing a single page of an infinite book? The theory offers a strange comfort, a guarantee that somewhere every potential is realized, every regret is undone, and every tragedy is averted. It is the ultimate multiverse, not of distant bubble universes with different laws, but of intimate, diverging copies of our own world, splitting from us at every moment. The cost of this elegant solution to quantum weirdness is an almost inconceivable extravagance, a reality of infinite duplication. Yet it presents a universe of relentless creativity, where nothing is ever truly lost, only branched, ensuring that every possibility, no matter how small, finds its own world to call home. That infinite branching of reality suggests every story is told, but the oldest story of all is written in faint, ancient light. This is the cosmic microwave background, the afterglow of the Big Bang itself. Imagine a photograph taken when the universe was a mere 380,000 years old, a glowing fog of hot plasma that filled all of space. As the cosmos expanded and cooled, that light was freed, and it has been traveling to us ever since, stretched by the expansion of space into the microwave part of the spectrum. When we map this radiation across the sky, we see a stunning, near-perfect uniformity. The temperature is almost exactly the same in every direction, a smooth sea of microwaves that stands as the strongest evidence we have for the Big Bang and the subsequent period of cosmic inflation that ironed out the early wrinkles. But look closer and the story grows strange. Embedded in this cosmic baby picture are subtle yet profound anomalies that challenge our simplest models. The most famous of these is called the axis of evil. It is not a malevolent force, but a nickname born from scientific surprise. When scientists analyze the patterns of hot and cold spots in the microwave background, they expect to find no preferred direction, a random distribution consistent with a universe that has no special axis. Instead, the data reveals a curious alignment. Some of the largest patterns appear oddly coordinated along a particular line through space, as if the early universe had a faint, built-in orientation. It is as if you spun a globe covered in random paint splatters and found they all vaguely lined up with the north-south poles. This alignment defies the cosmological principle, the core idea that the universe on large scales should look the same in all directions. Another deep puzzle is the cold spot. In a specific region of the southern sky, the microwave background temperature is significantly colder than the surrounding average. This spot is enormous, spanning billions of light years, and its statistical significance is hard to dismiss as mere cosmic chance. It is a vast, quiet chill in the universe's first light. What could cause such a feature? One explanation points to a colossal cosmic void, an immense region of space with far fewer galaxies and clusters than expected. If such a void existed between us and the cold spot, light passing through it would lose energy, an effect known as the integrated Sachs-Wolfe effect, potentially creating the cold imprint we see. Yet surveys have failed to find a void large enough to explain it. This failure opens the door to more exotic theories. Perhaps the cold spot is a bruise from a titanic collision in the earliest moments of existence. In the theory of eternal inflation, where our universe is one bubble in a frothing multiverse, it is possible for two such expanding bubbles to have gently bumped into each other. The energy released at that collision boundary could have left a distinct circular imprint on the CMB, a cosmic scar from a neighboring reality. Other ideas venture even further. The anomalies could be hints of a universe that existed before our Big Bang, a prior cosmic cycle whose final moments imprinted a faint structure onto our own beginning. Or they could signal topological defects in spacetime itself, relics from when the fundamental forces of nature froze into their current forms, creating cracks or textures in the fabric of reality. These whispers in the microwave static remind us that our origin story, for all its explanatory power, may still be missing crucial pages. The universe's first photograph is not just a portrait of birth, but a cryptic map, its faintest blemishes pointing to chapters of cosmic history we are only beginning to imagine. These cosmic anomalies exist on the very edge of our vision, but some of the most compelling mysteries are hiding much closer to home, in the gravitational shadows of our own solar system. For over a decade, a tantalizing pattern has emerged in the dark, frozen realm beyond Neptune. Astronomers tracking the orbits of small, icy bodies in the distant Kuiper belt have noticed something strange. A handful of these objects, known as extreme trans-Neptunian objects, do not follow random paths as you would expect. Instead, their orbits are curiously clustered. Their points of closest approach to the Sun, their perihelia, are grouped together in space, and their orbits are tilted in a similar direction. This is like watching a swarm of bees not buzzing randomly, but all making coordinated loops around a specific, unseen flower. The statistical odds of this happening by pure chance are incredibly slim. Something massive must be herding them, its gravity sculpting their long, looping paths over billions of years. This is the Planet 9 hypothesis. The proposed culprit is a world with a mass roughly 5 to 10 times that of Earth, making it a super-Earth or a mini-Neptune, a class of planet common around other stars but missing from our own neighborhood. Its orbit would be monstrous, a long, stretched ellipse taking between 10 and 20,000 years to complete a single journey around the Sun. At its farthest point, it would be over 20 times more distant than Neptune, drifting in a profound and perpetual twilight. This would explain why we have not seen it yet. A planet that distant reflects virtually no sunlight, and its orbital motion across the sky would be agonizingly slow, a crawl against the backdrop of stars. The hunt for Planet 9 is a monumental game of celestial hide and seek. Astronomers are using some of the world's most powerful telescopes, like Subaru in Hawaii, to scan vast, thin slivers of the sky where the planet's predicted orbit might lie. They are looking for a single, faint point of light moving against the fixed stars. The challenge is immense. It is like searching for a single charcoal briquette lost in a dark forest, using only the faint glow of a distant street lamp. Every new discovery of a distant Kuiper belt object with a peculiar orbit refines the search, tightening the net. Finding this ghost world would be a discovery of historic proportions. It would rewrite the story of our solar system's infancy. How did a planet that massive end up so far out? The leading theory is one of gravitational drama. In the early chaos of the solar system, Planet 9 may have formed much closer to the Sun, alongside the giant planets. A close gravitational encounter with Jupiter or Saturn could have flung it out on its extraordinary, exiled orbit. Its discovery would confirm that our solar system experienced a violent, dynamic youth, with planets playing a game of gravitational pinball that shaped the architecture we see today. It would also transform our understanding of the solar system's outer frontier, turning a supposed empty wasteland into a realm governed by a hidden, majestic giant. The search continues, a patient, meticulous scan of the dark, driven by the silent testimony of a few tiny, icy specks whose paths tell a story we are only beginning to read. The search for a hidden planet is a quest for missing architecture in our own cosmic backyard, but it rests on the assumption that our solar system is a common blueprint. What if it is not? What if Earth itself is a cosmic oddity, a one-in-a-trillion fluke? This is the rare Earth hypothesis, a sobering counterpoint to the dream of a galaxy teeming with alien civilizations. It argues that while simple, single-celled microbial life might arise relatively easily on many worlds, the leap to complex animal-level life, let alone intelligent tool-building beings, requires a staggering and improbable checklist of cosmic and geological good fortune. It suggests we are not living in a typical neighborhood, but in a gated community with impossibly strict entry requirements. The first requirement is a stable, long-lived star. Our Sun is a G-type main sequence star, not too big and not too small. Larger stars burn fiercely and die young in supernova explosions, not giving life enough time to evolve beyond microbes. Smaller, red dwarf stars are prone to violent solar flares that would sterilize any close orbiting planet with lethal radiation. Earth hit the stellar jackpot. Then there is our location, the Goldilocks zone, where temperatures are just right for liquid water to exist on the surface, but that is just the starting line. Our planet's remarkable stability is not an accident, it is a product of celestial engineering. Take our moon. It is unusually large for a planet of Earth size, the result of a cataclysmic collision with a Mars-sized body in the solar system's youth. This giant moon acts as a gravitational anchor, steadying Earth's axial tilt. Without it, our planet's tilt would wobble chaotically over time, leading to wild, unpredictable climate swings that would prevent the long-term stability needed for complex ecosystems to develop. Our large, molten iron core generates a powerful magnetic field, a planetary shield that deflects the solar wind and cosmic rays, protecting our atmosphere from being stripped away and life on the surface from being fried. This dynamo is kept churning by another geological gift, plate tectonics. Earth's crust is broken into moving plates that recycle carbon and minerals, regulating our climate over eons and preventing a runaway greenhouse effect like the one that scorched Venus. Even our solar system's layout plays a crucial role. The gas giant Jupiter, with its immense gravity, acts as a cosmic vacuum cleaner, deflecting or capturing many comets and asteroids that would otherwise bombard the inner planets with extinction-level frequency. Without this giant guardian, complex life might be repeatedly reset by impacts before it could ever gain a foothold. The rare Earth hypothesis compiles this list of fine-tuned conditions, a cosmic checklist where failing even one item could mean a world forever stuck at the microbial stage. It paints a picture of a universe where ponds of bacteria might be commonplace, but forests, oceans filled with fish, and skies with birds are breathtakingly rare treasures. This offers a direct and somewhat lonely answer to the Fermi paradox. The great silence is not because civilizations hide or self-destruct, but because civilizations almost never arise in the first place. The galaxy may be filled with living worlds, but they are worlds of slime and stromatolites, not cities and radio telescopes. We are not hearing from anyone because there is almost no one out there to call. This transforms our pale blue dot from a potential cosmic commonplace into something far more precious, a singular sanctuary of animal complexity in a quiet microbial cosmos. This cosmic checklist of fine-tuned conditions suggests our reality is a rare sanctuary. But what if our entire universe is itself just one member of a much larger, evolving family? To find that possibility, we must look back into the ultimate darkness, not as an end, but as a beginning. The terrifying singularity at a black hole's heart might not be a final stop. Some of the most imaginative theories in cosmology propose it is a gateway, a cosmic tunnel leading not to destruction, but to genesis. We have already seen how quantum gravity might replace the infinite point with a bounce or a fuzzball. But what lies on the other side of that bounce? One breathtaking answer is that every black hole is the birth canal for a new universe. In this view, when matter collapses to that ultimate extreme, the laws of physics as we know them are reborn in a new configuration. The interior of the black hole pinches off from our own space-time, forming a separate, expanding region, a baby universe with its own Big Bang. Our cosmos could be the offspring of a black hole in a parent universe, and every black hole in our own sky could be pregnant with a new reality, each with slightly different physical constants. This idea finds a profound expression in physicist Lee Smollen's theory of cosmological natural selection. It is a theory that applies the logic of Darwinian evolution to the cosmos itself. Imagine a multiverse where universes reproduce. Their method of reproduction is through the formation of black holes. Each new baby universe inherits its fundamental laws, its physical constants from its parent, but with tiny, random variations like genetic mutations. Now apply the cosmic pressure of natural selection. Which universes are the most successful, producing the most offspring, those that are best at making black holes? And what conditions favor the formation of many black holes? You need lots of stars, which requires elements like carbon and oxygen, forged in previous stellar generations. You also need stable orbits and the right balance of forces to allow galaxies to form. In short, you need a universe fine-tuned for the complexity that leads to stars, galaxies, and ultimately more black holes. Our universe, with its perfect balance for stellar formation, would not be a random miracle, but a highly evolved product of this cosmic Darwinism. We live in a universe that is a champion black hole breeder, and its laws are tuned for that very purpose. The eerie fine-tuning for life becomes a side effect of fine-tuning for stellar and galactic fertility. In this staggering vision, black holes are not tombs but seeds. Each one is a potential entire cosmos, budding off into its own dimensions, carrying forward a lineage of physical laws. We gaze up at the dark silhouette of Sagittarius, a star, the supermassive black hole at our galaxy's heart, and we might be looking at the ultimate cosmic parent, a silent engine of universal reproduction. This transforms the existential dread of the singularity into a strange kind of hope. The darkest objects in our sky could be luminous with possibility, each one a closed door in our reality that opens as a sunrise somewhere else, in a universe where the story begins again forever. That vision of black holes as cosmic seeds places our universe within an endless lineage of creation. Yet for life to arise within any of these universes, location is everything, not just around a star, but within the galaxy itself. We are familiar with the idea of a star's habitable zone, that narrow orbital band where a planet is neither too hot nor too cold for liquid water. But this concept has a much larger counterpart, one that stretches across light years of spiral arms and stellar clusters. This is the galactic habitable zone. It proposes that not all neighborhoods in a galaxy are created equal, and that the chance for complex life depends on finding the galactic sweet spot. Our solar system's position, about halfway out from the Milky Way center, may be part of a much rarer cosmic real estate than we ever imagined. The inner regions of a galaxy, close to the bustling core, are dangerous places. Here, stars are packed together tightly, like a dense urban center. This stellar crowding leads to frequent gravitational close calls, where a passing star can yank a planet from its stable orbit, sending it careening into the frozen dark or plunging it toward its sun. More critically, the galactic center is a factory for massive stars. These giants live fast and die young, exploding as cataclysmic supernova. In the inner galaxy, these stellar detonations are far more common. A nearby supernova would bathe any orbiting planet in lethal doses of gamma rays and cosmic radiation, effectively sterilizing its surface and stripping away its atmosphere. It would be like living next to an artillery range that never stops firing. For life to have the billions of years of stable, quiet evolution it needed on Earth, it must be sheltered from this constant cosmic bombardment. So we must move outward, but go too far into the sparse, quiet suburbs at the galaxy's outer rim, and you encounter a different problem, a poverty of elements. The story of our existence is written in elements forged in stellar furnaces and scattered by stellar explosions. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were created inside stars that lived and died long before our sun was born. These heavy elements, which astronomers call metals, are not evenly distributed. They are concentrated in the galactic disk, and their abundance drops sharply as you move away from the star-forming inner regions. A planet forming in the distant galactic hinterlands might be born from a cloud of primordial gas, rich in hydrogen and helium but desperately poor in the heavier elements needed to form rocky planets, complex chemistry, and ultimately, life itself. It would be a world without the fundamental building blocks for a rich biosphere. Between these two extremes, then, lies a narrow annular ring, the galactic habitable zone. It is a region far enough from the violent core to avoid frequent sterilization, yet close enough to the galactic center to have been enriched by generations of earlier stars. Here, a star like our Sun can form from a cloud laced with just the right mix of heavy elements. Here, orbital stability can persist for billions of years. Our place in the Milky Way seems to fit this description perfectly. We orbit in a relatively quiet spiral arm, shielded from the worst of the core's chaos, yet we are surrounded by enough stellar ancestry to provide the elemental wealth for our rocky planet and our chemical complexity. This theory adds a profound new layer to the rare Earth hypothesis. It suggests that even if a planet checks every box for local habitability, it must also win the galactic lottery, forming in the right place at the right cosmic time. A galaxy might contain billions of stars, but only a fraction of them reside in this life-friendly ring. This could drastically reduce the number of potential cradles for advanced life, turning the great silence from a puzzle into an expected outcome. We are not just on a rare planet orbiting a stable star, we are in a rare district of a vast and often hostile galactic metropolis, a quiet street in a safe neighborhood where the conditions for a long, complex story were just right. Our quiet galactic neighborhood offers a sanctuary for life, but the force that will decide its ultimate fate operates on a scale far beyond any single star or spiral arm. Dark energy, that mysterious pressure accelerating the expansion of space, holds our cosmic destiny in its grip. While the simplest model sees it as a constant, leading to the long, cold Big Freeze, there exists a far more dramatic and terrifying possibility. This is phantom energy, a hypothetical form of dark energy where its density does not just remain constant, but actually increases over time. Think of it not as a steady push, but as a cosmic pedal being pressed harder and harder with no floorboard to stop it. The consequence of such a force is not a slow fading, but a catastrophic cosmic unraveling known as the Big Rip. In this scenario, the repulsive force of phantom energy grows without bound. For billions of years, the acceleration would be subtle, much as it is today. But as phantom energy's density rises, so does its power. The acceleration would become self-reinforcing, exponential, and ultimately infinite. The first structures to feel this unbearable tension would be the largest bound by gravity. Galaxy clusters, those immense cities of thousands of galaxies, would be the first to be pulled apart. Their gravitational glue, which has held them together for over 10 billion years, would suddenly be worthless against the overwhelming pressure of space itself stretching at an ever-increasing rate. Next, individual galaxies would disintegrate. The Milky Way and Andromeda, destined for a merger in the far future under normal expansion, would instead be shredded from the inside out. Stars would be flung into the ever-widening void, their connections severed. Then the violence would come home. Within the last year before the final rip, our solar system would be torn asunder. The Sun's gravity would no longer be able to hold its planets. Earth would be ripped from its orbit, sent careening into the dark. In the final months, planets themselves would be pulled apart, mountains lifted from their foundations as the phantom energy's grip exceeded the planet's own gravitational binding energy. In the last inconceivable moments, in the final fraction of a second, the force would surpass the very bonds that hold matter together. Molecules would be ripped into atoms. Atoms would be torn apart, electrons stripped from nuclei. Finally, even atomic nuclei and the protons and neutrons within them would be shredded into quarks and beyond. The universe would end not with ice, but with a scream of infinite expansion, reducing all of existence to a thin, cold spray of fundamental particles, forever isolated and unable to ever interact again. This stands in stark, horrifying contrast to the Big Freeze, where structures remain gravitationally bound even as the universe grows cold and dark. In the freeze, our local group of galaxies might remain an island in the void for trillions of years. In the rip, nothing is safe, and the end comes on a swift, definitive timetable. So how could we possibly know which fate awaits us? The answer lies in precisely measuring the equation of state of dark energy, a number physicists call little w. This value describes the relationship between the pressure and density of dark energy. If W is exactly -1, dark energy is a cosmological constant leading to the Big Freeze. If W is less than -1, even slightly, it signifies phantom energy, and the universe is destined for the Big Rip. Our current best measurements from telescopes mapping the expansion history of the universe place W very close to -1, with error bars that still allow for the phantom possibility. The next generation of observatories like the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope aim to measure this number with exquisite precision. They will chart the expansion of the universe over the last several billion years in finer detail than ever before, looking for the subtlest hint that dark energy's strength is changing. The data they gather will write the final sentence in the story of everything. Will it be a long, quiet whisper into endless night, or a final, violent stanza of dissolution? The answer is out there, written in the accelerating flight of galaxies, a single number waiting to be found. The phantom energy of a Big Rip would erase all cosmic structure, but long before such an end, a clever species might leave its own indelible mark upon the universe. For decades, the primary tool in the search for extraterrestrial intelligence was the radio telescope, patiently listening for a deliberate signal, a cosmic hello. But what if other civilizations are not broadcasting greetings, or what if their technology operates in ways we have barely considered? The modern search has undergone a profound shift, expanding its vision to hunt for any detectable trace of advanced technology, any footprint left in the sand of the cosmos. These traces are called technosignatures. A technosignature is not a message, it is an artifact. It is any measurable phenomenon that reveals the presence of technology, whether its builders intended to be found or not. Think of it like this: if you were an alien astronomer scanning Earth from light years away, you would not need to decode our television broadcasts to know we are here. You might detect the peculiar chemical fingerprint of chlorofluorocarbons, our now banned refrigerants, polluting our atmosphere, a compound that nature is extremely unlikely to produce on its own. You might notice an unnatural glow on the night side of our planet, the collective radiance of billions of city lights and street lamps. These are unintentional technosignatures, the industrial exhaust of a civilization going about its daily business. This broader perspective turns every advanced telescope into a potential SETI instrument. Astronomers studying exoplanet atmospheres with the James Webb Space Telescope are now alert for more than just oxygen and methane. They are also watching for synthetic gases like nitrogen dioxide from combustion or complex industrial polymers that would stand out as glaring red flags in a planet's spectral data. The search for city lights focuses on the Terminator line of distant worlds, that razor's edge between day and night, looking for a pinpoint of unexpected brightness that electric grids would create. But technosignatures can be far grander than atmospheric chemistry. They could be colossal engineering on a stellar scale, like the incomplete Dyson swarm we imagined earlier. Or they could be more subtle, like the infrared heat signature of an entire planet whose energy use far exceeds what it receives from its star. Even the trails of spacecraft could, in theory, be spotted. An interstellar vessel using powerful propulsion, like a fusion drive or an antimatter engine, would produce an unmistakable plume of radiation and particles. While we could not see the ship itself, we might detect the brief, anomalous burst of gamma rays or the specific particles left in its wake, like the glowing trail of a speedboat on a dark ocean. The search methods themselves are becoming as innovative as the signatures they seek. Optical SETI no longer just listens, it watches. Powerful telescopes are equipped with ultra-fast detectors designed to catch brief, intense laser pulses that could be used for interstellar communication or even to propel light sails. A civilization might use such a laser as a lighthouse beacon or for spacecraft propulsion, flashing it for mere nanoseconds. Our instruments must be ready to catch that blink. Other researchers are scanning vast archives of astronomical data, using machine learning algorithms to sift through the light curves of millions of stars, searching for any irregular dimming pattern that does not fit the known profiles of planets or dust. This is how we found Tabby's star, and it is how we might find something even stranger. Perhaps the most intriguing frontier is the search right here in our own solar system. The theory of directed panspermia suggests someone might have seeded life itself, but a less dramatic possibility is that our cosmic neighborhood contains silent artifacts, ancient probes, or discarded technology from flybys that occurred millions of years ago. Projects like the Galileo project are systematically scanning the skies for unusual interstellar objects like Oumuamua, and even proposing missions to intercept the next one that passes by. They also advocate for rigorous scientific study of unidentified aerial phenomena, not as proof of aliens, but to ensure we are not overlooking a physical artifact in our own backyard because it seems too extraordinary. This evolution from listening to comprehensive astronomical detective work reflects a deeper maturity in our thinking. We are no longer just waiting for a phone call. We are surveying the entire cosmic landscape, reading the light, the chemistry, and the energy of distant star systems, looking for any clue that someone, somewhere, built something. It accepts that intelligence might express itself in ways we cannot yet predict, and that the evidence we find may be subtle, ancient, or utterly bewildering. The universe may not be shouting its secrets, but if we look carefully enough, we might just find its fingerprints. This search for fingerprints in the cosmos rests on a bedrock assumption that our memories and perceptions connect to a real and continuous past. But what if that assumption is the greatest illusion of all? The Boltzmann brain paradox is a thought experiment that emerges from the cold equations of thermodynamics and cosmology, and it leads to a conclusion so unsettling it threatens the foundation of rational thought. It begins with a simple, well-established fact. In a universe that is eternally expanding toward maximum disorder, a state called heat death, random fluctuations can still occur. Given enough time, the random jostling of particles in the void could, by sheer accident, assemble anything: a teacup, a Shakespearean sonnet, or a fully formed, self-aware human brain complete with a lifetime of false memories. These hypothetical, spontaneously generated observers are called Boltzmann brains, named for the 19th century physicist Ludwig Boltzmann, who first grappled with the statistical nature of entropy. The paradox arises when we apply probability to the ultimate scales of time and space. In an infinitely old or eternally inflating universe headed for heat death, the chaotic void will exist for a literally endless duration. The odds of a random fluctuation producing a single, conscious brain with a coherent set of memories are astronomically small, but they are not zero. Given infinite time, such an event becomes not just possible but inevitable. In fact, it should happen an infinite number of times. Conversely, the odds of a fluctuation producing an entire, ordered, 13.8 billion-year-old universe like ours with galaxies, planets, and a continuous history are unimaginably smaller. The statistics deliver a bizarre verdict. It is vastly more likely for there to be a universe filled with countless, disembodied Boltzmann brains popping in and out of existence, each believing itself to be a person in a real world, than for one like ours with its consistent structure and deep past to exist. Therefore, if you are a conscious being pondering your existence, you are statistically far more likely to be a momentary Boltzmann brain, a ghost of order in the chaos, than a product of a long-lived cosmos. Your memory of reading this sentence, your feeling of a chair beneath you, the entire history of the universe you recall, all of it would be a perfect, convincing fiction generated in an instant, only to dissolve back into the formless void a moment later. This is not a scientific theory in the traditional sense, but a devastating logical paradox that highlights a crisis in our cosmological models. If our best picture of the universe's eternal future leads to the conclusion that we are almost certainly illusions, then something in that picture must be profoundly wrong. Cosmologists take this paradox seriously because it acts as a razor, cutting away models of reality that lead to such absurdities. One major way to avoid it is to reject the idea of an eternal future heat death. If the universe does not last forever in a dormant state, but instead eventually cycles or resets through a big bounce or a transformation of dark energy, then the infinite time required for Boltzmann brains to dominate never materializes. In a cyclic universe, the era of complex, ordered structures like galaxies and planets is not a fleeting statistical fluke, but a recurring phase, making embodied observers like us vastly more common than disembodied phantom minds. Another solution lies in the very beginning of everything, the theory of cosmic inflation, which sets up our universe with such low entropy, may have created conditions where our kind of ordered reality is the typical outcome, not the extreme exception. If the inflationary process naturally produces bubble universes like ours with high probability, then we are not an unlikely fluctuation but a standard product of the multiverse. In this view, Boltzmann brains are the true oddities relegated to the remote, decaying corners of eternity. The paradox forces a humbling confrontation with the limits of knowledge. It asks how we can trust any observation, any memory, any law of physics if our own existence could be a statistical mirage. The very act of doing consistent science over decades, of building telescopes and finding evidence that fits into a coherent story of cosmic evolution, becomes our strongest argument against being Boltzmann brains. A fleeting fluctuation would not discover the expanding universe, the cosmic microwave background, and the fossil record. It would simply hallucinate them without internal consistency. So we press on, using the continuity and predictability of reality as our anchor, trusting that the universe we measure is telling us a true story, and not merely the convincing dream of a brain that formed from chaos 5 minutes ago. The Boltzmann brain paradox remains the ultimate warning from the edge of cosmology, a reminder that our maps of reality must lead us to a place where we, the mapmakers, can logically exist. The ultimate test of our reality may lie not in grand cosmic structures, but in the hunt for a single, elusive particle that should exist everywhere, yet remains nowhere to be found. This is the mystery of the magnetic monopole. Every magnet you have ever held, from a simple refrigerator magnet to the compass needle pointing north, has two inseparable poles, a north and a south. Break that magnet in half and you do not get isolated poles. You simply create two new, smaller magnets, each with its own north and south. This duality seems to be a fundamental rule of our world. But our deepest theories of physics scream that it should not be. In the quest for a grand unified theory, a single framework that describes all forces except gravity, physicists found a mathematical necessity. These elegant equations predict the existence of a particle with only one magnetic charge, a solitary north or a solitary south. This would be a magnetic monopole, a fundamental magnetic charge as basic as the positive or negative charge of an electron. Finding it would be as revolutionary as discovering electricity for the first time. More than a curiosity, the monopole is a direct relic of the universe's first moments of unimaginable unity. In the searing heat just after the Big Bang, when the electromagnetic, strong and weak forces were fused into one superforce, the fabric of reality would have crystallized with topological defects like cracks forming in ice. These defects would manifest as monstrously heavy particles, the magnetic monopoles, each carrying a titanic mass perhaps 10 quadrillion times that of a proton. According to the math of grand unification, the hot, dense early cosmos should have been a factory for these particles, churning them out in staggering abundance. There should be so many left over that they would be a dominant form of matter in the universe today, and we should be tripping over them constantly. But we are not. we have never found a single definitive magnetic monopole. Their glaring absence is one of the most significant puzzles in modern cosmology. It means something in our story is profoundly wrong, or that something intervened to sweep them clean from our cosmic neighborhood. The leading solution is the same theory that solved the horizon and flatness problems: cosmic inflation. That brief, hyper-accelerated expansion of the universe just after the Big Bang would have stretched space-time so dramatically that it would have diluted the density of primordial monopoles to virtually zero. Imagine a single drop of ink in a thimble of water. That is the dense concentration of monopoles in the early universe. Now, inflate that thimble to the size of our entire observable cosmos in a fraction of a second. The ink drop is stretched into a faint, imperceptible haze. Its particles spread so thinly they become effectively impossible to find. Inflation elegantly explains why our local region of the cosmos seems to be a monopole desert. The hunt, however, has not been called off. Scientists are searching for these cosmic ghosts with ingenious methods. Deep underground in old iron mines, massive detectors wait for the unique signature a super-heavy monopole would leave as it plows through matter. Others have looked for traces in ancient mica crystals, geological samples that could have preserved the damage track of a monopole passing through Earth over millions of years. Even the Moon has been considered as a potential capture site for these relics. The search itself is a form of cosmic archaeology, digging not in soil, but in the predictions of our most ambitious theories and the silent testimony of the cosmos. Finding just one magnetic monopole would be a discovery of Nobel Prize-winning magnitude. It would provide direct experimental evidence for grand unification, offering a breathtaking glimpse into a time when all forces were one. Its continued absence, meanwhile, is a powerful, if indirect, pillar supporting cosmic inflation. The monopole is a ghost particle that haunts our equations, a missing piece of the puzzle whose very disappearance helps us map the shape of reality's first fleeting instant. That missing magnetic monopole leaves a void in our physical equations, a silence where a particle should be. But perhaps the most profound silence of all is not in what we cannot find, but in what we are. We have journeyed through theories of hidden matter, cosmic inflation, and simulated realities, yet one final idea turns the entire quest inward. It suggests the ultimate answer to space's biggest mysteries is not out there in the cosmos, but within the very act of looking. This is the participatory anthropic principle, the radical notion that consciousness is not a late arriving passenger in the universe, but the fundamental reason for its existence. The seed of this idea is planted in the unsettling bedrock of quantum mechanics. In the famous double-slit experiment, a particle behaves as a spread-out wave of possibilities until it is observed or measured. At that instant, the wave collapses into a single, definite particle at a specific location. The standard interpretation is that the measurement apparatus causes this collapse. But the participatory anthropic principle asks a deeper question. What if the observer is not just recording reality, but completing it? What if the universe only takes on definite properties when a conscious mind interacts with it? In this view, the cosmos existed for billions of years before life as a shimmering fog of quantum potential, a story without a plot. It was only with the arrival of the first conscious observers that the fog condensed into the solid galaxies, stars, and planets we see today. The past itself, from the Big Bang onward, retroactively crystallized out of possibility to create a consistent history leading to the observers who now look back. This concept was championed by the physicist John Wheeler, who coined the phrase "it from bit." He proposed that every particle, every field, every event in the universe derives its ultimate reality from the answers to yes or no questions, from bits of information. And these bits only become definite when elicited by an observation. Imagine the universe as an immense cosmic book that is only written as it is read. The pages are not pre-printed. The narrative of cosmic evolution from the first instant to the present day is being authored in the very moment we perceive it, with our consciousness providing the pen. This is not suggesting humans magically dreamed up dinosaurs and supernova. Rather, it posits that a universal quality of observation, perhaps inherent in all sentient beings, is the mechanism that translates quantum possibility into classical fact. Variations of this idea stretch from the rigorously mathematical to the deeply philosophical. Some interpretations link consciousness directly to the mechanism of quantum state reduction, the moment the wave function collapses. Others see it as a more general cosmological principle, where the universe's laws are fine-tuned for life because life is the necessary ingredient to bring those laws into full being. Without an observer to define it, the universe remains an unrealized potential, a song waiting for an ear. This transforms the earlier idea of the fine-tuned universe. It is not that we are lucky to be in a universe that allows us. It is that a universe cannot truly be said to be at all until beings like us are there to say it is. Mainstream physics largely relegates this to the fringe, and for good reason. It borders on metaphysics, placing consciousness outside the system we are trying to explain. It is notoriously difficult, if not impossible, to test scientifically. How could you design an experiment to see what the universe was like before there were any observers? Critics argue it puts the cart before the horse in a spectacular way, making the intricate, complex phenomenon of consciousness a prerequisite for the simple existence of atoms and light. Yet, for all its problems, the participatory anthropic principle stands as the ultimate expression of a mystery that has threaded through every theory we have explored. From the holographic principle storing information on boundaries to the simulation hypothesis rendering reality upon observation, a common thread emerges: the intimate, inexplicable link between the observer and the observed. It is the final, dizzying loop in the cosmic mystery. We look out into the vastness of space, searching for answers in the light of distant stars, only to have the universe quietly suggest that the search itself is what gives those stars their light. We have traveled from the fine-tuning of physical laws to the event horizons of black holes, from the silent watch of a cosmic zoo to the quantum spark of a universe observing itself. 30 theories, each a doorway into a deeper mystery. Some are grounded in hard data, others dance at the very edge of imagination, but together they map the breathtaking landscape of human curiosity. They remind us that science is not merely a collection of answers, it is the relentless, courageous pursuit of questions. It is the act of staring into the abyss and daring to propose a shape for the darkness. Whether dark matter is a particle or a revision of gravity, whether we live in a multiverse or a simulation, the value lies in the search itself. This journey of inquiry stretches our minds, challenges our assumptions, and humbles us with the scale of what we do not yet know. That is the true engine of discovery. So here we are on a pale blue dot, surrounded by a silent, accelerating cosmos filled with invisible matter and driven by an unknown energy. We are creatures of stardust who have learned to decode the light of distant suns and to question the nature of our own reality. In this vast and mysterious theater, we are both the audience and the actors, trying to understand the script of a play that seems to rewrite itself with every observation. The universe does not owe us easy answers, but it has given us the capacity for wonder, and that may be the greatest gift of all. Now we turn the question to you. Which of these cosmic mysteries pulls at your imagination the most? Is it the haunting silence of the Fermi paradox, the mind-bending implications of the holographic principle, or the eerie possibility that we might be living in a simulation? Share your thoughts in the comments below. Let us continue this conversation among the stars. If you enjoyed this deep dive into the universe's biggest puzzles, subscribe for more journeys to the edge of understanding. And never stop looking up at the night sky with that same timeless sense of wonder. The next great mystery is waiting.